Able to see my screen?
Yes, I can see.
Thank you so much. So welcome everybody. We are Women Coding Community. We believe in building a safe environment for women to grow and lead in tech. Our mission is to empower women to be at the forefront of technology and innovation. And our vision to achieve this purpose is to empower women through education, mentorship, community building, and career services. We conduct workshops and events. We connect members with industry mentors. We have a supportive community, and we have meetups and conferences. We also share tickets to conferences and tech events through raffles. And we always raise awareness and promote inclusive industry practices. We are a very inclusive and supportive community. We follow a code of conduct, which is very important to us. You can visit our website to check the code of conduct. And it is important for us that we treat each other and communicate in a professional and respectful manner. If you see any issues with the code of conduct, or if you have any questions, you can write to us via email, london@womencodingcommunity.com. We have several projects. One of them is mentorship program. We have three types of mentorship: long term, which is for a year; ad hoc, that is monthly; and study groups, like the one you're in. We have also book club, writing club, speaking, career club, coding club, and also CV clinic for having CV reviews, and also mock interview groups. We also have open source projects like the platform project where we're building the next version of our website. Apart from that, we also have study groups like system design, this one, and lead code study group, machine learning, and also cloud related study groups. You can join us as volunteers. Volunteers are always welcome to help and work with us to achieve our mission. Currently, these are the opportunities that we have. You can help us and support us in coordinating and organizing events. You could give a tech talk. You can contribute to our open source projects, our community blog, newsletters, and support our programs, different programs in any which way possible, irrespective of what background you come from. So please do join us as a volunteer. And here's the QR code. You can scan for that, or you can visit our website and register as a volunteer. The benefits of being a volunteer in Women Coding Community are that you will have a very friendly crowd, excellent networking opportunities, and also an opportunity to add some recognition in your CV and LinkedIn profile. You will not only learn technical skills, but also soft skills and leadership skills. Like mentioned earlier, you can get tickets to events and conferences, and above all, a great and very supportive and inspiring community to be with, work with, and learn from and be inspired from. So please come and join us and help us in our mission. Thank you very much. We'll share the link to our website and our Slack later, so you can join us. Thank you. And before I hand over the mic to Shailaja, I'd like to just take a picture of the attendees here. If you don't mind, you can switch on your cameras, although it's not obligatory if you're comfortable. So I'll just wait a few seconds for everybody to turn their cameras on. Okay. Okay. There we go. Thank you. I'm going to start recording this session now, just so you all know. Okay, this session is being recorded. And Shailaja, now I hand over the virtual microphone to you.
Okay, thank you. Let me present my screen. Hi, is everyone able to see my screen?
Yes.
Okay. So last week we covered the partitioning techniques and we were in the middle of the consistent hashing. And this time I have come up with a better example to show how consistency hashing is different or better than the normal modulo hashing. Before starting on that, I first wanted to explain the motivation behind the consistent hashing compared to normal typical modular hashing and the advantages of that as well. So in having very high overview, you can get a logical understanding even before jumping into the consistent hashing mechanisms. So we saw a typical modular hashing, how it works. For example, if we have a set of key ranges and set of nodes, let's assume I have a 0 to 9 as the keys, hash keys. After taking the partitioning index and I hash it, let's say the resulting range is 0 to 9 in this example, and the number of nodes are 5. So the modular hashing result would be from the key 0 and 5 will go to the node n0, key 1 and 6 n1, so on. Now, this is a mapping with the modulo hashing when there are 5 nodes and the keys are 0 to 9. Now, if node 0 fails, let's assume one node is failing. In that case, if you see the number of nodes are becoming 4. That means when you're doing percentile modulo of number of nodes per a key, the resulting mappings, if you see, almost most of the mappings have changed. That means if we have a let's say in this case, if we are having couple of partitions and initially when initially before all nodes were up, when initially you planned the hashing mechanism for your partitioning, this is how keys are going. 0 and 5 are going to this one, 1 and 6 are going to this one, 2 and 7, 3 and 8, 4 and 9 here. But if one node is failing, then we need to redistribute the data. But how the redistribution is changing? Almost 5, the data are 5. If this one is failing, so both these keys have to be redistributed. Not only that, the data on other nodes which were alive, which are perfectly fine, even those keys need to be redistributed. So if you see the here, 1 and 1 has to be going to n1, which is the same as before. 5, which was here, it will move to the n1 here, and then 6 move to the another node n2 here. So if you see the most of the data, not only the data which was there and the node which were failed, the other data also has to be redistributed. And the redistribution of the data is very costly because we need to read the entire data from the disk, and over the network, we need to move it to the copy to the another node and then update the mappings accordingly. To avoid this, that's where the reason we are coming to the consistent hashing. What we are doing the consistent hashing here, the objective is, instead of depending on the number of nodes, the hashing mechanism, instead of depending on the number of nodes, we create fixed number of partitions. That way, we simply say that there are, let's say, 10 partitions, and then going to the 5 nodes, then this is a fixed mapping. There is no modulo percentile that we apply. This one. Okay. So we create fixed number of partitions, and after that, when a node fails, we only redistribute the data which is existing on the node which was failing. So in this case, instead of redistributing the data which was which is there in other nodes, we only redistribute the data which is on the failed nodes. And also another advantage we do in this approach is instead of having a bulky partitions, in that case, for example, if each partition 0 and 5 are quite bigger, in this case, instead of if we redistribute the data, 0 probably going to this node and 5 probably going to another node, we try to make many smaller partitions. So let's say assume these are instead of 2 partitions made into 5 or 6 partitions, then we move the part of the smaller partitions into different nodes. That's how When the one node fails, we are having an advantage of distributing the data to all alive nodes on almost equal proportions. That's with that way, we are not overloading any couple of nodes. We are not creating a skew. For example, in this case, if each partition is, let's say, 1 TB, and when this node fails, when we move 1 TB here, 1 TB here, this is getting additional data or additional load, reads and writes as well, along with the existing loads they already having. Instead, if we create 5 partitions, each of around, let's say, 0.4, let's say, in this case, each node will take 0.4 of the size, and each node will have the equal extra load, so we are not creating the skew. That's actually motivation behind the consistency hashing. Now, how we are going to do this in the consistency hashing? Let's assume, usually if you see after hashing the hash key value, the hashing of the parsing index. Let's say in the Java, when you hash a value and the hash key with the resulting hash, when you store it in an integer, the resulting value can be from 0 to 2 power 64 minus 1. So the hash range can be, the hash range here, in case of, for example, typical Java system, it can be 0 to 2 power 64 minus 1. In this example, we are just assuming 0 to 23 for simplicity, because we can't really draw such a huge lane here. Assuming that, now let's assume we are having 3 nodes, N1, N2, and N3. We are simple consistency hashing without virtual nodes. What happens? When we place nodes on the ring at virtual random locations and the tokens, that means there is no physical ring as such. The simple hash table, which is from 0 to 64, that we assume that virtually like a ring, and then from the 0 to in this case, there are 24 tokens in total. 24 by 3, totally 8 tokens for each of the node. So all the tokens belonging to in this range go to N2. All the tokens belong to in this range go to N3. All the tokens belonging to in this range go to N1. So that means when the request is coming, let's say partition primary index is, let's say, user ID, and user ID is 1, 2, 3. Let's say after hashing, the resulting hash key value is 3. Then 3 comes here. When we are in the system, what we do check, we make an on-the-fly calculation. Is 3 in which range is it? If the 3 is in the range of 3 to 7, then go to node 2. If the key value is in this range, we can go to N3, otherwise go to this node. That is how the logical is implemented. Now, with this approach, if you see the N1 is failing, if the N1 fail and completely not recoverable, in that case, what happens? All the load which was going to N1 is now going to N2. So that means the existing load of the N2, which was here, and the new load here, both of them are going together to N2. Now N2 is taking the double the load. The 16 keys it is taking, whereas N3 is taking 8 keys only. That means when a node is failing, the redistribution is not even. It's creating the skew and making some of the nodes overloaded compared to other nodes. That's the reason we try to implement the strategy, as I mentioned before, creating multiple small partitions instead of few bigger partitions. And that is one thing. And here, the virtual node means there is, in case of virtual node, what you can assume, like if there is a one node here, which is N1, I will just use this pen. Just assume one node here, which is N1. You can logically partition them like a virtual disk, say all a C drive. In the case of, for example, Windows, so all a C drive is virtual node NC1, let's assume. D drive, you can say ND1, so on. So you can partition your disk into a set of smaller portions and then assign the keys accordingly. In fact, we are in real systems, you don't really need to do that. Any of the virtual data can go anywhere. But for your understanding, I'm mentioning that you can just assume that virtual node in a system is a abstraction of a portion of the storage space, or the in case of the load incoming data, it's a portion of the incoming request. You can assume so. Now let's here, if you see, um, N1, one virtual disk is here, one another virtual node is here, another virtual node, another virtual node. N2 similarly is having 4. N3, sorry, N3 I showed, my eyes are not good. N2 is here. So when we are creating virtual nodes of the real system, placing in multiple locations, the advantage we see now. Let's assume if N1 failed. If N1 failed, it means all these virtual nodes are failed. In case, if for example, this entire N1 machine is down, that means even any portion of the data on the N1 can't be accessible. That means all these virtual nodes are also failing here. So when it failed, what happened? The load, which were the 22 and 23, which were before going to N1, now going to N3. And here 2 and 3, which were going to N1 before, were going to N2. And similarly, other cases. So it means if you see, the load taken by other nodes is almost equally proportional. It need not be equal all the time, but it's not as drastic enough as to create a skewing. So if you see, the N1 data went to N3, and here it went to N2, and if you see here, it went to again N3 twice, and again if you see, it went to N2 twice. So that means both N3 and N2 nodes have taken equal proportion of the data of the older, the node which died. In real systems, based on how the nodes are placed, we need not be always equal, but at least good enough. The algorithm is good enough to avoid such drastic skews. That's how the consistency hashing works. Now I will take questions on the consistency hashing before going on to the indexing.
Shailaja, so sorry, I didn't understand like N1, N2, N3, right? We've distributed them. I didn't understand why they're repeating in that circle, firstly.
Okay. Let's assume that's how the virtual nodes are called. Virtual nodes means those are not real nodes. So we are trying to act one node as multiple nodes. So for example, if you I just want to place the same node in multiple places, but I just want to create a different token for each of the instances. It's like I will just show you. There is one node N1. There's just one node N1. But I want to take different ranges. So here, this is token. Let's assume here the token, which is between 23 and 0, T1. Here the token is between 3 and 4, T2. Here T3, and here T4. Okay. Now I want to assign 4 different tokens to the same node, so that I can, when it fails, its data goes to different nodes, different virtual nodes on the system. So what do? I just create, not really physically, you don't need to create. Physically, you don't need to really make any partitions or any specific places in the specific portions in the actual node. The nodes remains the same N1 data, but it takes data from different token ranges now. So from T here, the node before T2 and before T3, the tokens before T3, T4, so on. So for all these tokens, it has to take the data. So what we are doing in the metadata, when we create, we are saying that the 22, 23 has to go to N1. We don't say the range, actually, we just say the token. Oops, T1. T2 has to go to N1, so on. So that's how we are mapping the N1 in multiple times in the token range. So that's the reason we just call them as a virtual nodes. Those are not real nodes. The reason why virtual nodes, because we can create as many such instances as possible. In this case, I have created 4 instances. You can create 40 as well. So did I answer your question?
Right. So this is consistent hashing. You're saying that is, you take any node and you create, you basically put it on different points of the circle,
Yeah.
and then map a token to the node, and whenever it falls in the range before that, it will go to that node. Is that right?
That's correct. So previously with a virtual node, one node was taking only one token. That means any range before that token, it was taking.
Yeah.
Now the same node is taking multiple different ranges, and it need not be consecutive. Need not be. It can be anywhere on the token on the ring. So
Oh,
that's the reason we are asking that node to pretend like a multiple nodes, not like a one node.
okay, okay, that makes sense. So you're saying that if we treated it as one physical node, then it will only one copy of it will exist on the ring, and then the disadvantage of that is if, let's say, another node fails, a huge range of data will come and fall into that node, right?
Yeah. Physically, it's still only one node. Only that in the when we are abstracting, we are not telling the system that this is just only one node. This is acting like a multiple nodes. Just consider it like a multiple nodes. Thus, we are just doing everything in the software. Physically, we don't need to do any of the virtual nodes. In
Right.
fact, you can do in the virtual disk, for example, when we are mounting file systems on the typical machines, you can mount different disks as a different file systems. And for the outsider, it looks like those are different storage systems. But underlying is the same machine, it's just a different disk mounted as different file systems. So that can also you can use as a node, and we call it as a virtual node.
Right, right. It is just, I think the idea is mainly further what do you say, dividing the partitions inside each node.
Yeah, to try to have multiple ranges for the same node distributed randomly across the ring, such a way that if it is consecutive, then all the data, this has to take quite bigger range. Instead, we want to place n1s in different places. So not in this kind of strategy, when n1 is failing, multiple nodes are taking the load, not, because there are multiple smaller ranges. That's how we are creating multiple smaller partitions.
That actually makes sense now. So one last question: what is the maximum node failures this kind of system can tolerate?
The coming to the node failures, it depends on the number of replicas. So in this case, to make the design simplified, I didn't draw the replica. But for example, if the number of replicas is at 3, so the number of nodes we can failures we can tolerate is related to replica is the redundancy. For example, if we are having um, 3 copies, then even if 2 copies fail, you can still access the data from third copy. If there are 4 copies, even if 3 copies fail, then you can access from the fourth copy. So the tolerance is depending on the redundancy, and how much more redundant data you have, the more tolerance you can have.
Okay, okay, that makes sense. Thank you very much.
So go ahead,
Sorry to
please.
interrupt, Shailaja. There are two more people raising hands for questions. Do you want to take
Uh,
them now?
yeah, sure, please go ahead. Should I open the queue? Okay.
No, okay. Roshni, you can go now, and then maybe Irene.
Yeah. Thank you very much. Just wanted to ask this question. Uh, with the consistent hashing methodology, would the range scan be less performant than the range-based partitioning?
So there are two things to this. First thing is anything hash based indexing you do, that will destroy the range capability. That is the one thing, because the moment you're doing hash, the original data, even though, for example, the range 1, 2, 3, you take, even 1, 2, 3 are consecutive, the moment you do the hashing, which introduces the anonymousness into the hashing methodology, the resulting hash values can be very random. It could be 1 probably going to the hash v10, 2 probably going to 200, 3 probably going to 3000. So the moment we do any hashing mechanism, the range capability will go away. But there are systems like Cassandra, they try to take both of them. So I will show you one example. Actually, we have that in the discussion a bit down, but I will just show you that how it happens. So usually for systems like Cassandra, I don't know about the DynamicDB, what they do, the partitioning key is one which is using the hashing. Then we have another key called sort key, the cluster C, whatever you call. That extra key that will not be used for the hashing. That means, I'll show you one small example here somewhere. I think I have written. Okay, yeah, here it is. So what happens? Let's assume you're using user ID as the partitioning key. And so in the consistent hashing or even the normal hashing, you take the user ID, hash it. The resulting key, for example, 100. And he has another user ID, so on. And in the partitioning key, you can mention the sort key. What if, for example, let's assume we can take it as a order ID. Okay. So when the hashing is only based on the user ID, so this is a partitioning key. This is only based on the user ID. Only user ID used for the hashing. So we won't be able to run any range query on the partitioning key, the user ID. But because already used as a sort key, for example, order O1, 100, you did multiple orders, let's assume 100, O3. But because the part after partitioning, after applying the hashing, the resulting hash key is the same for the same user ID. The resulting hash key is the same. Though you can't run range queries on the user ID, you can run range queries on the order ID. In this case, order ID is not actually a good one. Example, let's say I say timestamp T1. If I assume that timestamp as a this one, for example, as a sort key, then time T2, time T3. Now we are having order IDs as well, let's assume. Then you can, the query is coming as what give me all the orders this user has made from this time to this time. Then you will give the, you need to give exact user ID value. You have to say that user 1, 2, 3, and for the timestamp T2 to timestamp T3, what are all the orders he has made. This one is exact value you have to give, because that's when you go to the, you hash it, you go to the 100. And then in 2 to 3, this can be a range. So we go and read the range of values here belonging to the given query. So now whenever any hashing mechanism is introduced, the range capability has gone. But we try, the system tries to take advantage of the range by these kind of mechanisms, having some additional columns which are not part of the hashing mechanism. Did
But
I
that
answer?
would not be part. Yeah, very good. Just checking. So this would be not part, not the sort key would be only used for the range queries, but not determining the partitioning logic. Is that right?
That's correct. So
Okay.
we have the primary key. The primary key can be, for example, user ID and the timestamp. Sorry, my impression is gone. So in that case, we tell them that partitioning key is only user ID. We have the way in the create table, we can have a syntax saying that user ID is a partitioning key, while the primary key is this one. And then the remaining, whatever is not is the partitioning key, is taken as the sort key, and we can apply range query on that part. But any queries, to be efficient, we must provide the keys part of the partitioning key, because that's the only time, if we are providing, that's the only time we can go to the exact partition where we want it to go. Otherwise, we have to go and read from the multiple partitions if we don't know what is a complete value of the partitioning key.
Oh, so the client must provide the partitioning key at the time.
If the query need to be
Okay.
efficient, if the query need not be efficient, then you can just select star as well. No one is going to stop you. Even the database is not going to stop you. You can simply say that get me user IDs in the values from 1 to 100. You can say that, but the query to be efficient, that means it is faster. It doesn't go into multiple partitions, do the scatter gather. Then for that to happen, you need to provide the partition key values.
All right. Thank
But
you,
yeah, this is for the systems like Cassandra, DynamoDB, which are using the consistent hashing. But if you go to some of the traditional databases, for example, Teradata, or I don't know about the Oracle much, but they use B-tree method of B-tree kind of partitioning keys. I don't know about exactly how Teradata Oracle does, but usually I see some of the traditional databases, they use a B-tree method. In case of B-tree method, we use the trees. That means the range capability is not gone. In that case, even on the partitioning key, we will be able to run the range queries.
All right.
So that's a, you need to, when you're doing POC of which database or which storage systems you wanted to use for your system design, you in practical systems, usually we run the benchmarks for your use case. That's the reason, even though, for example, Postgres is very efficient, to say, but will not be efficient for your particular use case. There's a reason you always need to run the POC, take the benchmarks and see for your use case, is it good or not. Otherwise, you probably need to remodeling of the data, the table schema, such a way that it is efficient for your use case.
Good.
Yeah, what is another question? I think I see another
Hi
one.
there. Hi there, Shelley. Thank you. Just a quick question. So the hashing function decides which partition your data is going to be stored in on the ring. My question is, how do you know where to place the nodes on the ring? And sorry if I've missed it and you've already said, but that's the bit I missed.
Sorry, can you please repeat the question?
How do you know where to place the nodes on the rings? The virtual node, the actual nodes and the virtual nodes? Because they don't seem to be in order.
Yeah, so that the end user doesn't need to know that, but the system, for example, if you take Cassandra or whatever, DynamoDB, whatever, they do have a routing layer as well. So when a request is coming, when the system when system is starting up, the Cassandra, DynamoDB is starting up, then those systems probably they have algorithms. Even manually also you can mention where to place which node. So I can, if for simplicity, I'm taking them manually. I'm telling that the Cassandra put all nodes from 20 to 23 on N1, all nodes from there is a configuration file. You can say something like AML file, or I think it's not AML, some other configuration file, where we can say that these are the ranges. These ranges, these number of keys, you put it on the N1. For example, starting from 0, number of keys 22 has to go through N3. So this kind of metadata map, you can give it to the system. When it is booting up, when the system is coming up, it will create this kind of ring internally that you can't see. You can't see that until you are having access to the configuration files and the system as an admin. You won't be able to see this one. So if for you, it doesn't matter. When the request is coming, let's assume I'm trying to access user ID, user 123. And I just send it to the any node on randomly. Again, there are different methods. Some for now you say that you can just assume that the DNS layer. I take IP address, ask for IP address of a server. It can give any IP address. For any of the nodes, it can give any IP address. We take that IP address and ask in this case, for example, let's say N2, the data is in N1, let's assume. Ask N2, the key is the hash, this is the value, user ID 123. Then what does N2 do? It hashes user ID 123. Let me use. It hashes 123, takes the hash key value, let's assume it takes the hash key value 2. In this case, I just assume 3 as we had thought before. Then it sees that, okay, 3 belongs to the N1. So here there are multiple strategies who is going to handle this request. For systems, some systems, when they see 3 is belonging to N1, they reroute the request to N1, ask the N1 to process the request and send the response back to the user, or response back to N2 and it sends the response back to the user. But some systems like Cassandra, what they do, they don't have any particular node as the owner. They just they take N2, they send, if the consistency is 3 minimum nodes, that means at least 3 nodes has to say that this is the answer. Then it will send requests to randomly 3 different nodes, takes the responses from 3 nodes, then checks what is the latest value based on the version and timestamp, and returns the response back to the user. So for the end user, simply saying, this is my partitioning key value, give me the data. This is my query, this is my where class, give me the data. But the node, they are having a routing strategy, and they're using the configuration files. Using the routing strategy, they decide which node this request has to process, on which node this data exists, and they redirect the data, take the response, and send it back to the user. Did I answer?
Okay. Thank you for that. Thanks.
Okay, so are there any more questions on the consistent hashing, because we are going into the indexing mechanisms? Okay, if there are no more questions, I'm going to the indexes. Okay. So indexes, actually part of this we already discussed, but I will still explain. So for the primary index, if you see different systems are having the value, different primary, sorry, do we call it primary index? Primary key, you can call it primary key. The primary key you usually use no, right? So that when you create a table, you tell that what is the primary key. The primary key has to be in queue for every row in the system. If it is a user ID, every user is expected to have a unique user ID. Otherwise, it won't be a primary key because we get a unique constraint error. From the primary key, some systems do allow you to define what is the partitioning key value, what is not part of the partitioning key value. So the example that I showed, partitioning key value need not be unique key all the time. So there is a difference between primary key and the partitioning key. I'm saying that my primary key is, let's say, user ID and the timestamp. I'm using the same example as before because it actually is the same answer as well, kind of. This is my primary key. This entire together is unique. For every row, this is unique value. But partitioning key can be only this one. It need not be unique. For example, as I showed in the previous example, it can be user ID 100 more probably having multiple orders, then we are probably repeating the same for multiple rows. So if you see complete primary key together is unique for every row, but just if you look into the partitioning key, it need not be unique. This is one kind of systems. There are some other systems where primary key is not mandatory. So you can just create a table and don't declare any primary key. In that case, they have different mechanisms. They create, they select, there's which one, they have their own way of choosing which column need to be a partitioning key. There are some systems which you don't need to mention the primary key, but you can still mention the partitioning key. That's still applicable for the Cassandra. You can say that I don't need a primary key, but this is my partitioning key. That means it doesn't expect there to be any key column for every row, but you can tell that this is a column. So I don't mention this. This is the partitioning key. I say that. Then it just simply takes this one for the redistributing the data. So the difference between primary key and the partitioning key. Partitioning key is a column or the set of columns which is used for deciding on how to distribute the data to the different partitions. Whereas the primary key is just a unique key constraint, unique key set of columns. All columns together need to be unique for each and every row. And partitioning can be part of the primary key value, but need not be all the time. You can have a different key altogether selected as a partitioning key. Is that clear?
Sorry, what is the purpose of primary key? I didn't understand. Like a different, and I understood what partitioning key is. That is, it's used for distributing the data, but I didn't understand what's the purpose of primary key and what it means.
Okay, so any table when you create, most of the times you wanted to avoid, for example, duplicate duplicate rows. For example, if you wanted to ensure that when you are inserting data to the table, you wanted to ensure that just take a simple example. There should be only one order ID. I mean, different row in an orders table should have a different order ID. Okay, that's obviously the same. The services which are creating the orders are supposed to, the order services which are creating the orders supposed to create a different order ID for every incoming order request. But for example, the service, there are multiple distributed services running. The order has come here, it is generating order ID, and there is because of the load balancer mistake or the client reconnection or the timeout, whatever, the same request has coming here, or there could be bug in the services code itself. If these are generating a different order, same order ID for different orders, order O1, order O1 for the different orders, or even by mistake creating duplicate orders, in that case, you want your table to detect it immediately, even before letting that happen. So what you tell when creating a table, you say that create table orders, and the primary key is the order ID. Now, when O1 is inserted, initially table happily takes it. The moment another O1 is trying to insert it, it immediately bans this, saying that okay, there is already another O1. Oh, sorry, couldn't share. Okay. So there is another O1 already, and your uniqueness constraint is not meeting. So that means for database is just helping you to avoid creating duplicate rows by mistake. So that's the reason primary key is not mandatory for all the databases in all the tables. It's user's choice. User can choose it. So primary key is something nothing to do with the partitioning, nothing to do with the data distribution. Just from the end user, as a developer, you are creating a table. You want to restrict something to be unique. That's what primary key is.
Right. It's to protect the system from generating multiple. I mean, repeats the values. So
Yes.
one other question: you said that partition key need not be unique, but you mean that the columns within the let's say a partition key is made up of 3 columns, right? So you are saying that when you say it need not be unique, you are saying that for a certain column, it can have a rule that it is not unique. Is that right? Or what do you mean by when you said it need not be unique when we have a partition key?
Yeah. So the primary key, you know why we wanted to have unique constraint, because as a developer, you wanted to detect any problems happening in your system immediately. But most of the time primary partitioning key is partially at least part of the primary key, because most of the times in use cases, we provide primary key value in the access pattern. In this case, if you take the order ID, or most likely when we are reading the data as well, you know that most likely you're providing in the where class order ID O1. So for example, order is this one, get the data. Order is this one, get the data. So because it is most used access pattern, primary key data access based on the primary key is mostly frequently used access pattern. Most of the times we try to retrieve the partitioning key as part of the primary key. Could be complete primary key or part of the primary key. That's mainly because access based on the partitioning key is faster, efficient, and most of the use cases require access based on the primary key. That's the reason these are partitioning key is something physically impacting. Primary key is something just uniqueness constraint, but because of the access pattern, those are kind of interrelated. But it need not be for all the tables. For most of the tables, this is a criteria.
The criteria that we use primary key as part of the partition key, right?
It's other way around. Partitioning key as part of the primary key, because primary key probably is need to be unique. It probably we are adding more columns to that. But for the partitioning key, it can be just half of the primary key. It can be just few columns of the primary key. In this case, for example, I wanted to see all the orders O1, O2, O3, all order IDs. And I want to, most probably I will be having a range queries. Let's say when I open my Amazon homepage, I will mostly see last 6 months of the orders, right? So most of the use cases based on the get the order. In this case, user ID. Okay. For my user ID, U1, get all the orders placed in the last 6 months of the time frame, T1 to T6. So this is the most used access pattern. Then and also we usually create timestamp and user ID as the primary key, because we wanted to create only one order for any particular timestamp to avoid any duplicate orders by any chance. In that case, the partitioning key can be only the user ID, but the timestamp can be extra one to ensure the uniqueness of the primary key, and also to be able to retrieve based on the range on the timestamp. So let's say primary key probably having many columns, but the partitioning key can be just part of that. This is the partitioning key. It can be full complete as well. So you can whatever the most based on the access patterns, you can define how to make it more efficient.
So I have a question again, sorry. So you said that querying with partition key is faster because
Yes,
data is already nicely distributed according to that partition key.
exactly.
Right?
Correct.
So if I, let's say, now use primary key, which defines the uniqueness of the values to read data,
Hmm.
uh, I'm assuming that becomes slower because now that additional columns is now probably repartitioned within the same node, for example.
No, no, because those are not part of the partitioning key. Those are all located together in the same partition. Even if those are not located together, still we are hitting the only one partition. Let's say the sorry, you get partitioning key order is the already the sorry user ID. Simple, make it simple. User ID is the partitioning key, and the timestamp is the not part of the partitioning key timestamp. Okay. Now, when you give user ID, this user ID is going to only single partition. So when you hash a U1, you know that it is going. You don't need to read this partition at all. So you're reading only one partition. In the one partition, the user E1 is most likely those rows could be together. Even if by chance not together, if those are located in different locations within the partition, still your query is faster because you are hitting only one partition, most likely one disk or maybe couple of disks within the single partition. You don't need to go to another partition at all. So
Okay.
that's the reason, even though primary key, complete primary key is not used as a partitioning key, still the data access is faster. But only as long as you provide complete value of the partitioning key value. If you don't provide this one, no, it's not going to be.
So one other question here. What was I gonna ask? Uh, Okay, so you said that one of the reasons to create a primary key, even though it's not mandatory in some databases, is to ensure that the service is not duplicating some values. Now, if we have a primary key which is more than two columns or more than one column, actually, how does it ensure that? Does it still ensure that there is uniqueness involved? Because like that, you know that. That table creation thing you wrote, create order ID, it is
Yeah.
primary key.
So primary key, with the moment you say a set of columns are primary key, the database always ensures those are unique, regardless of how many columns did you use. And it need not be always primary key. You can simply say unique constraint. Some databases, even though some columns are not part of primary key, you can simply say that ensure unique constraint on these set of columns, and database do ensure that this is the part of the constraint framework of the database. And regardless of are those part of the primary key or not, are those part of the partitioning key or not, database always ensures the constraint.
But that uniqueness is not per column, right? For example,
It's
if let
it is when you have multiple rows, let's assume, and only these columns are part of primary key or unique constraint, then what database ensures the value together here and the value together here are not same. The
yeah,
value here O1, and still these are different, then that's fine.
okay,
Database to allow that. Value here U1, then yes, as long as these two are, database do allow that. Here, the moment it is same, database immediately will flag you unless it is different. So how database ensure that it takes value completely together, hashes this value, takes the hash value, let's say
yeah,
hash h1, and when the new data is coming for another row, it takes this value, makes a hash and checks is it the same hash value or not. If
yeah.
it is the same hash value, it says that okay, if there is a unique constraint, you cannot do that.
It compares the checksums. Sorry, one last question. What is the
Okay.
what is there any disadvantage of making the primary key very large? Like, for example, sorry, partition key very large. For example, instead of choosing two columns, let's say the table has 8 columns, and I want to make 6 columns up as part of the partition key, so that my Because the reason I'm asking is because I know that my users will query the table always with these 6 columns, right? So I can make my querying reads much faster when my partition key is equal to primary key. So if I have a very large partition key, is there any disadvantage?
No, because the advantage for in this case, right, when the write request is coming or when the read request is coming, as long this incoming request, the request is already having the required columns. So it doesn't have to go to the, let's say you are having very big partitioning key. These values, as long as we don't have to read it from the disk, those are in memory. When request is coming, it is in memory. The what system does, it takes these values, does the hash, whatever the consistency hashing, whatever the hashing methodology, it does that. Then we'll go and access the corresponding data. So for the system, when it is doing this checks, whether to write, where to write the data, where to read the data, all the required columns are in memory. So it doesn't have to do any extra work. There's a reason there won't be any impact and performance impact, the drastic performance impact on this one. Even in the read case, as long as you're providing all the values as which are part of the partitioning key, then these values are in memory. It doesn't have to go anything from the disk, so it is going to be faster. But if you're only providing a partial partitioning key, in that case, it cannot be efficient because there are some missing columns which are part of partitioning key. Then system doesn't know which particular partition it has to go. It will go and read on all the partitions.
Yeah, I mean the case where now let's say a read request came. My question was, you have to read from the disk. Now you can the system calculated a hash. It knows, okay, my data is on node 2 based on this hash key. The partition is stored there. So it goes and reads from N2, right? Now the two possible cases are, if my partition key was 6 column long, and my primary my query is also 6 column long. So if I design my system like that, it's very easy because I have to just go straight to one node and it knows the data and reads out. But let's say, like you said, if that was only if my query had 6 columns and only 3 columns out of that were partition key, then I have to first figure out, still will it be slower? That's what I'm asking.
No, as long as you provide complete partitioning key, it won't be any slower, because no matter how many columns you have in the request, if you're having all, if you're providing all the partitioning key values, it creates a hash value out of it. So if you have 10 columns in the partitioning key, the hash value going to be from 0 to 264 minus 1. Or if you have a one column as a partitioning key, is going to be the same. After hashing, the resulting key value is going to be smaller, simpler, and it will always go to the single partition.
Okay, yeah, that makes sense. Thank you.
Are there any questions? If you would it be all right if you limit the number of questions per person? Okay. Yeah, does anyone have more questions? Please feel free to ask if you're having questions, because I'm not planning many questions. Sorry, no, I'm not planning a lot of content in one session, so I can take more questions in each of the session. If no one is having questions, I will go with the secondary index. Yeah, so secondary index as well, partly we have discussed in the last time. Space for this one. So as I mentioned, because there can be only one primary key and only one partitioning key for a table, but sometimes we probably having multiple access patterns. Most of the time we try to have the majorly use the most access pattern as the primary key and part of the partitioning key, but there can still be other set of columns we probably access. For example, if I take simply a table with the user ID and order ID and the timestamps, let's assume. But if I wanted to to be more sensing, let's assume a location to make it more sense. Location, usually the multiple rows probably having the same location: UK, France, or UK, and so on. When I have an access pattern, let's say I want to see all orders made from the location UK, or all the orders made from location France. Let's assume I'm having a periodic thread every 5 minutes is going and retrieving this information from the table and displaying on the dashboard. Let's assume. So it's running every 5 minutes. That means it's frequently used, but it's definitely not part of the partitioning key because it's not as frequently used as the user ID or ID basis. And also there can be only one primary key. In this case, what you can do, you can create a secondary index on this location column. So when you create a secondary index, the physically what happens in the database, this is the original table. This one, if let's assume you're having it, assume so. This is the original table. The database creates another hidden table that you don't see. You don't know that there is another hidden table. It simply points when you create a secondary index on this column. It creates a location column for this one. For all UK, for corresponding rows in the table, it creates the references, or you can say pointers, R1, R10, R20, so on. Similarly, for the France, it has more rows, R2, R12, so on. So when the query is coming based on the UK, instead of directly hitting the original table, the query will first go to the, because this is database understands that there is a secondary index on this location table, location column. So I can utilize it for the faster access. It will go and look into the secondary index table, maps, retrieves the corresponding matching row, takes this original actual tables row IDs from here, and then go on read from the actual table. So this how in this case, if there is no secondary index, assume this secondary index is not existing. In that case, what you have to do, you have to read the complete table. We don't know where is UK all the rows related to UK located. They need not be consecutive. They need not be consecutive to run even a range query all the time. In that case, so we have to read the complete table, then filter out the based on the location. That's going to be a complete table scan, which is very, very not efficient. Instead of this one, you know the row IDs. The moment you know the row IDs, you will get the row IDs means the hash values of the those rows. You take those hash values, you come directly go to the original table corresponding to that row and read the original table. So if you see, in this case, where the database is reading two tables, one is a secondary index table, the other one is the original table. But still, it is faster than not having a second index because it is avoiding reading complete table, reading all the partitions and the tables data and all the partitions, then do the filtering. Instead of doing all that, we are still utilizing the hashing mechanism by going into this table, locating those row IDs and going to the original table. So this is going to be faster. Not as faster as using a partitioning index, but still faster than the complete table scan. The read's going to be faster in this mechanism, but the write's going to be slower because whenever the original table is changing, then we then we need to go, the database need to go and check if the corresponding row in the secondary index has to be changed. If it has to be changed, it has to modify. For example, for the row at 10, if it assume this row is deleted, new row is created for the location UK, then R11 has come here. So every time I need to delete from here and insert a new row from it to the here. So we need to make updates. So we need to make two table updates every time one original row is changed. And there can be many second index up to 126, 128, depending on system. And there can be many such hidden tables. So a single row update in the original table may result in many table updates in the database. But this is fine for the SQL systems, usually relational databases, because relational databases are usually read heavy. So they are fine with compromising a little at the right side for having the higher throughput read side. Whereas in the systems like NoSQL systems, I wouldn't say everyone, but most of the NoSQL systems are usually write heavy. In the case of write heavy, they don't want to take this penalty of having secondary indexes. So many of them don't support the secondary indexes. Some of them do support different kind of secondary index. There are two kinds of secondary indexes. One is called local secondary index, other local index, other one is called a global index. So what is the difference between local index and the global index? For example, this is a one partition and we are having a original table, let's say. In this case, location UK, location France. The local secondary index maintains references to only rows which are locally existing on the same partition. So UK, it says that row R1 and so on, R1, and let's assume another row R3 UK, then it maintains R3. There is another partition and the same table distributed there having R5 UK, R7 UK. The secondary index on this partition 1, this doesn't have references to the partition on this other partition. Instead, it will have its own local secondary index, UK. None of these are visible to you, the end user. These are all in the system only. So it takes care of that, but you need to understand this to understand the performance penalties. Okay. So this is a local secondary index here, S2. This is local secondary index, S1. The main advantage of this approach is, so when you are coming the request, when there is a write operation going on, when you new row insert, you insert here, it will go just update in the same partition. You don't need to touch other partitions. Similarly here, but when case of read operation, you need to do the scatter gather. So you send request to all the partitions, read these rows from the second index, local index here, take the references, go and read the actual rows. Similarly here, do the same operation here. Then you get answers saying that, okay, R1, R3 here, R5, R7. Then you match the results. And if there is any filtering need to be done, do the filtering and then return the response to the end user. So in this case, read can be having some performance penalty because of the scatter gather involved. Whereas the other option is global index. In case of the global index, what happens? Let's say you're having, I'm trying to draw a bigger one so that I can write it numbers. Otherwise, I can probably use the same diagram to make it easier. So in this case, what happens? The secondary index is global. That means it will have references to all the related rows in any partition. So here R5, R7 also, which are not R5, R7 are existing in this partition, but still are part of the secondary index on the partition P1, whereas actual rows are existing on the partition P2. Similarly, if let's assume there is a France, in the France, the actual row is here R3, it will be having pointer in the other partition. With this approach, what happens? When you are having a reads, the main reads will have an advantage here. You take you need to read only one partition, take all the row IDs, then you directly issue the reads because you already have hash values. When you issue the reads, all the original data need to be read from the multiple partitions, but you will directly go to the corresponding hash values. You don't need to do the filtering or scanning there. But the main problem is the writes gets impacted, because in case of the writes, what happens when any write happen to this partition also have to update it in the secondary index of the other partitions. So this is a local and global index, but the most of the systems already pre-decided should they use local index, secondary indexes. There is no option for us as end users to choose that. But when you are choosing a system for your design, you can you can understand how those backend systems are working and do the trade-offs.
We have two people raising hands, Roshni and
Okay.
Tatiana.
Yeah, go ahead. Please go ahead.
Hi, just a quick one. Where do we store this global index?
So
Um,
these are all on the same partitions as it is. You can assume the global index is same like a original table, but partitioned differently. So this its partition is simply like creating another table, but the partitioning index, the partitioning key is the location here. But this is all done internally in the database. You don't need to do, but the impact is the same as creating another table with the just two columns. One is the partitioning secondary index value, the other one is the hash ID values, and the location is as the partitioning index. In that means this table completely is a table, but the partition based on the location value. So it is still stored internally in the same across the partitions in the storage system. For you, it's a simple internal table, hidden table. Just that partitioning key is different for these hidden tables.
so it'll be a kind of a duplicate of all the indexes across the partitions, and it will be there in every partition. Is that what you're explaining? Let's say
Uh,
R1, R2, R5, and R7 are all situated in all the partitions separately. So it's like a duplicated, redundant index. Is that what you're saying?
Redundant means here you are making the only location value redundant, not entire row. You don't make entire row as a redundant. So I'll show you a simple example. So if, for example, if you're having a table, you created a table, table, and the location as a one column, and list of hash values, or you can say that hash values are typically long or integers, whatever, as in their column, and you mentioned that partitioning key is location. So when you create this kind of table, how the database distributes this data, the same way the secondary, this is the exactly schema of the secondary index table, but system has created it for you, you didn't create. And partitioning key is a secondary index column. The secondary index column is the partitioning key. So when you create this, how the data is distributed on the different partitions, it will go and put part of the table. So it says that UK rows are all here, France rows are all here, and this value is repeated. The secondary index value is repeated. This is existing in the original tables as well, and the secondary index, but the actual entire row is not repeated because we are putting only the hash values of the partitioning key of the original data. So entire row is not repeated. For example, the original R1 probably is very big, probably it is having 100 columns, but your secondary index is having only 2 columns, not 100 columns.
R1 means the record in it itself.
The record number.
Oh, okay.
It's like a which partition number, table ID, partition number, row number. That's something internal to the system.
Okay, I thought R1, when I said R1, it was just a key. The key is what I meant. But yeah, understood. Thank you.
So it's a kind of pointed address of the original row where it is existing. So you can directly jump to that row instead of going to the entire table.
Yeah. Thank you.
Are there any more questions on the secondary index or any of the topics we covered so far? Yeah, I will give you suggested readings. I will share a pointer. Rajeshri, do we have any?
We have one. Yeah, I mean, it was planned for 1 hour, but it's okay. You can continue. We have one more person raising hand, Moina.
Okay.
Yeah, hi.
You go ahead.
I have two questions here. Firstly, the difference between local index and global index. You said that in local index, this this virtual table that tells you the index, it's present on every node. So when a read request comes, it has to hit every node, and that takes time. But in global index, there is only one table that maintains the index of all the nodes, and then you just hit that one node to get the answer. So I want to know, where does the global index, which node does the global index maintain?
Okay, so I think the answer is kind of opposite. So when in case of the local index, it's like I will give a very abstracted example so that you can understand better. Let's assume for all the people in UK, we are maintaining an index within the UK. That means there is a record table ledger which is maintaining all the people in UK's identities or whatever. For all the people in US, they are maintaining their own index which are local to within the US. Let's assume that. Now, when there is a request to get the data related to people in UK, we just need to look at the local ledger. We don't need to go look at the US ledger. So the local requests are faster. We just look at the local ledgers and okay, these are the people, this is the data. Whereas similarly, if the requests in the US are only related to US, then they are faster. They don't need to contact UK administration and get the data, so it's faster. But if there is any request in UK related to US, then it will be costlier because it has to be cross region. But in case of local index, this won't happen because the database understands that where is this data located. When the request is coming for US, it automatically knows that it has to go to the UK location, not for the UK. So any local region requests are going to be fine, but write operation is going to be painful. For example, if in the UK, if anyone is giving information related to US, then we need to go to the US record and update it, not in the UK. So the write operations gets impacted. Whereas in case of the global index, you're having single ledger for entire UK and US together. So any operations happening, the mainly advantages, write is going to be faster because if someone in US is trying to update UK information, we can just update locally there. We don't need to come to the UK and update ledger here and the other way around. But the reads may get impacted. For example, in US, if someone is trying to read the UK information, we take their local ledger, but that local ledger, we take the UK information and then the original data record ID, we take the original record ID and then we go and hit the UK database to read that original information. So it's going to involve multiple partitions. One is to read the index value from the US and then read the original data from the UK. Is it abstracted enough? I tried my best.
Yeah, but okay. I think I understood that if this is geographical, division of data, that's the case. But let's say do we solve these problems within the same data set? I mean, for one data center where you have distributed nodes and how you partition the data, now you have to create indexes. So let's say my cluster has 5 nodes, right? So how do I mean, and all those 5 nodes are in the same region. Do we do indexing in such a case where all these 5 are on the same data center?
But this is particularly related to partition, not at the data center level. If the nodes are within the data center, out of the data center, doesn't matter. The partition, just the partition, we call it. Let's say one node, 5 nodes are 5 partitions in the data center here.
I mean, I just said data center, but let's say the problem is within the same region that you want to maintain indexing for all the data that's coming to UK, that is written to UK and read from UK. So how do we solve the problem of indexing, local indexing and global indexing, if all the data is only in UK?
If entire UK is a single partition, then it's with the local index, both the secondary index related to UK. I think I am a bit confused here.
No,
So
what I mean is, it's not single partition. I have large amount of data for the UK region, and I have let's say 6 nodes to distribute data of all the UK data on 6 nodes.
Okay, 6 partitions. So 6 nodes, 6 partitions. Okay.
Now my question was like, how do you do local and global indexing just for UK region with these 6 nodes?
Okay, so one thing is you don't have option to choose between local index or the global index most of the times, because this is pre-implemented in the database. For example, Cassandra only supports local index. Relational databases supports most of the relational database supports global index. As an end user or even as a database developer, you don't have option to choose. They have decided based on performance, what kind of performance they want, what kind of workloads they want to support. For example, in Cassandra, for them, eventual consistency is fine. So for them, if the right operation is happening in this partitioning, the local index slowly catches up. That is one thing, and across cross partitioning operations are costly. So there are many different reasons why Cassandra chose they always support local index. They don't support global index. I don't think I'm not aware of any databases giving you an option to choose. So the reason why I'm explaining this to you, because you don't have option as an end user, you don't have option to choose. But when you understand, when you're doing you're making your system design and you wanted to have a trade-offs of which one to go, and what is important for you, is the write latency important to you, is read latency important to you, is secondary index important to you. Those cases, if you have an understanding of this concept, you can choose the right one for your use case. That's the reason I'm explaining. But we don't have option to choose most of the time. They're pre-implemented.
Okay, so so I think the point is that based on how the database is implemented and what my use case is, I would choose that kind of a database, whether, like you said, consistency matters or availability matters or whatever.
Yeah, but you can have you can have your application to implement very similar strategy as a secondary index, where you can choose how you want it to do. For example, I can create another table instead of data asking database to create a secondary index. I want to say that my secondary index, and create a column location and the row IDs hash values. And whenever my application, my service updating the original, I will go and update the secondary index, my secondary index table as well. That means the same logic you can apply, you can implement the way you want to, but the databases usually don't give an option for you.
Okay. Sorry, I said I had two questions, but just last question, which is second one. Where you showed UK R1, the R1 was just the row ID. Is that what it is?
Okay, so R1 is usually the row ID, you call it, is usually hash value that we generate after applying the primary on the partitioning key. For example, partitioning key is user 1, 2, 3 and timestamp T1. Okay, we're not using timestamp till now as a primary key. Then once you apply the hashing on that, you get a, let's say 3 is your hash value. Then R1 is the most, it's usually 3, but if it is not a local index, if it's a global index, you have to mention which partition. Let's say P4, P3. So P4 hash value 3, something like so. That's database. So whatever information database needs to directly go to the row here instead of going through the all the different partitions. So it could be different data center. If it is different data center, say the DC2 and the partition P4 and the hash value 3. So whatever it requires to locate, it kind of directly offset into the correct row. That information is the row ID. So this is something different from each of the systems based on how internally they are implemented. You can just assume that is a row ID, which is unique for every row, and you can directly hit the row using that row ID.
Okay, thank you very much.
Are there any more questions?
I think we can wrap the session for today, Shailaja, because I think we've already crossed the timing. So maybe if there are any further questions, I hope it's okay if they contact on Slack, Shailaja.
Yeah, sure. They can contact me on the Slack. A couple of people also reached out.
Okay.
For these indexes, I will have separate sessions later on.
Okay. All right. Thank you very much, everybody. And if you have any further questions, feel free to reach out on Slack. Thanks for joining and see you next week.
Thank you. Oops.